this video, we are going to talk about double integrals over a rectangular domain. In a follow-up video, or the next video, we'll talk about general domains. This is our first overview slide, and this is our second overview slide. We will go through the overview slides fairly quickly, and then we'll back up and go through each topic in more detail and with more examples. In this video, we are going to talk about the double integral over a rectangular domain. We start by thinking about the physical interpretation of the double integral as a volume. We extend the idea from one variable calculus that integrals give us an area. So like when we integrated between a and b f of x dx, that we interpreted as the area under the curve between a and b of f of x. So this curve is our f of x here, our function. In multivariable calculus, double integrals will give a volume. So let's say f of xy is z. So here are values of x, here's values of y, and we'll have a rectangular domain in this video. And in our next video, we'll extend this to just general domains. So then let's say we have this function here hovering above, so z is hovering above. So for every value of x and y, you find a point in z until you finally have this surface. So this is your domain. Then we will say that the area under this surface over the domain will be our double integral. And our double integral can be noted or denoted several ways. One, you could do the integral r being a region of f, or you can say integral over a region, f of x dA, and this gives you a hint that here, instead of dx, which is just along the variable x, dA means it's an area, so you have the hint that it's two-dimensional, that your domain is two-dimensional. Or you can be more explicit, and you could say over r, f of x dx dy, or the most explicit you could do is you have limits of integration. In this case, x will go from a to b, f of x dx, and y will go from c to d. So an example is the integral over r, x squared plus y dA, where r, our domain, is the square 0, 1, 0, 1. So in other words, we're going to integrate x squared plus y, where dx, x is going to go from 0, 1. Oh, this is our domain, x is 0, 1, y goes from 0, 1. Or in 3 dimensions, right, x goes from 0 to 1, y goes from 0 to 1, and we have this rectangular domain. So x goes from 0 to 1, y goes from 0 to 1. We do our integration here with respect to x. So we consider y a constant. So then we have 1/3 x cubed. If y is a constant, that's just going to be xy. And we plug in our 1 and our 0, and we get 1/3 plus y. Now we integrate with respect to y. So here we get 1/3 y and 1/2 y squared, plug in our limits of integration, and we get 5/6. And another way of viewing this is when we integrate this over our r, we can think of this first integration. Remember, when we integrate with respect to one variable, you're getting an area. So here, when we integrate between x equals 0 and 1, we can think that it's like holding y constant. For a constant value of y, we're going to get this area in the xz plane. And then when we integrate through y, we're basically just then summing up all these areas for y equals 0 to 1, and then you'll end up with a volume. We're going to look at Riemann sums for these double integrals, and first I want to remind you what they were like in one variable calculus. So you had this function f of x, and then you had your x, and you could divide up your x into these subintervals. So if you want to integrate, say, from a to b, you can divide up a to b into subintervals, and then you would then calculate the area of the box. So you would either use this point or this point as your height, and you would basically estimate the area under this curve by summing up the areas of the rectangles underneath. And as you broke up x into smaller and smaller intervals, eventually you would be approaching the actual area under the curve. In the same way, when we do our double integrals, we're going to look in our domain, instead of these different, breaking up our a to b into intervals, we're going to break them up into closed rectangles. So we're going to partition our domain. So we're given a closed rectangle from a to b and c to d. So x goes from a to b, y goes from c to d. We're going to partition R, this rectangle, and it's going to consist of two collections of partition points that break up R into a union of n squared subrectangles. So the idea is here, you're going to divide up your interval in X into n partitions. They don't have to be the same size, but here's like one partition, here's 2, 3, 4. This is what it would look like if we partitioned X from A to B into 4 partitions. Over here then, we'll also partition y equals c to y equals d into 4 partitions. So we have one partition here, 2, 3, and 4. So when we partition x and y into these subintervals, our domain gets partitioned into these rectangles. So that's what this idea is here. So delta x now, for delta xi, so let's say delta x1, that's going to be delta x1 minus, in this case, this would be delta 0. So it's this length here. Whereas y, if we're looking at delta y1, that's going to be y1 minus y0. So that's this height. So what you get then is this rectangle with the width delta xi and height delta yi. That's this note here. Now suppose f is any function on our a to b, c to d, and we partition R in some way, then let Cj be any point in the subrectangle, so any point inside. Then the quantity, the sum, if we sum over all of the, for each partition, some height, we take kind of a random height in the rectangle, and we multiply it by our area. A sub ij is the length of the partition times the height of the partition, then what we get is our volume there. And this is our Riemann sum corresponding to the partition. And so if we take the limit as we let x sub I and y sub I, as we make these partitions smaller and smaller, this is going to approach our integral over here. So our integral is the limit. Last, we have Fubini's theorem, which tells us it doesn't matter if we integrate with respect to y first and then x, or if we integrate with respect to x first and then y. That was our quick overview, so now we'll go through everything in a little more detail and with more examples. The first thing we'll do, we'll give you a physical interpretation of double integrals, and in particular, double integrals will give you a volume. To see this, we'll step back and look at one variable calculus, where we had integrals gave us an area under a curve. So if you recall, in one variable calculus, we would integrate over a domain, so in x, and we would let x vary from a to b, and we would include the endpoints a to b. And then what we would be doing is we would look at the function f of x, which is the height of the function. F of x is the height of the function at x. So we thought about, we used Riemann sums, and then we took the limit as our spaces between the rectangles got smaller and smaller, and essentially we were adding up, the integral was adding up all of these heights. And in effect, what that gave us was the area under the curve f of x from a to b. So it's this area here. Similarly, now, in vector calculus, we're going to have our variables x and y, and we'll have a function of x and y that gives us a surface z that hovers over the xy plane. So we're going to integrate over the domain, so we're going to let x vary between a and b and y vary between c and d. And then when we evaluate the integral, we're going to look at the heights z over our rectangular domain, and we're going to be adding them up. So essentially, we're going to get the volume of under the curve f of xy over the rectangle in the xy plane. We denote these double integrals as f of r being the region that we're integrating over. We can also say integrating over the region R, f of x, y, dA with respect to the area of the region. We also have integral R, f of x, y, dx, dy, giving us a little bit of the idea that we're taking small, like Riemann summed kind of things. And then we can also switch, this should have switched the order of the integration dy dx. Oh, I see. This notation emphasizes the fact that it's a double integral. You integrate over x first and then over y. So this is the double integral. The double integral is implied here by the r and the dA or the dx dy, giving you a hint that it's an area, and r you would know would be a region as opposed to an interval. But this notation is probably the most explicitly clear. We'll talk a little more about this physical interpretation, but for now we'll do a quick example just to keep things from getting too abstract. So in here, our region R is going to be the square 0, 1 to 0, 1. And often, especially for double integrals, we focus on graphing and understanding what's happening in the domain. And then we understand that above this domain, there's some other function hovering over. So we're going to integrate x from 0 to 1, and the y values are also going to go from 0 to 1. So that's the 0 to 1 dx. That tells us where x is integrating. And then y, dy, is integrating from 0 to 1. And we're going to integrate this function, x squared plus y. And again, think of this function, f of x, y, hovering over your rectangle that you're integrating. And here we're just looking at the xy plane. So then to integrate the inner part of the integral, the dx, we're going to treat x as the variable, y is just considered a constant. So this evaluates to 1/3 x cubed plus y times x, and we are evaluating between 0 and 1. So we plug that in, and we get 1/3 plus y, and now we have the integral, the outer integral here, 0 to 1 dy. So now y, we're integrating with respect to y. So we have 1/3 y plus 1/2 y squared, evaluated at 0, 1, and our final answer is 5/6. And just to kind of reiterate our double integrals, we work from the inside out. So we start with this, we focus on this integral here. The dx reminds us that we're integrating with respect to x, so y in this case is considered a constant, and we're going to evaluate between 0 and 1. Once we get that integral done, then we work on the outer integral here, and again here. Our y reminds us that now we're integrating with respect to y. Another look at this integral, giving a little more support to the idea that the double integral is a volume, is when we look at the inner integral, when we're only looking at when we're integrating with respect to x, essentially what we're doing is we're holding y constant. Remember I said, oh, we're going to treat y as a constant. So essentially we're holding y constant, and then for all values of x, we're summing up the heights f of x, y, or we're summing up the function f of x, y. So we're basically doing this one-dimensional integration, and we're going to get an area for one value of y. So that's what's happening in this inner integral. We're getting an area because we're holding y constant, and we're summing up all these heights. Then when we go to the outer integral, what we're doing is we're then just marching along the y-axis, and for each value of y, we're going to hold that constant, and we're going to integrate another area. And then eventually, as y goes from 0 to 1, we have all these cross-sectional areas that we're adding up, that we're summing up here in the outer integral. And that will give us a volume. Our second and final slide for kind of our overview of the topic concerns Riemann sums, and is essentially the definition, or how we also come to view this as a volume, the double integral as a volume. And I'm going to start this again with this little drawing over in the corner from one variable calculus to remind you what Riemann sums look like in one variable calculus. So if you have an integral from x equals a to b, then we would divide up this interval to, in this case, I just divided it up into 1, 2, 3, 4 partitions. And then for each partition, I chose a point, and For this Riemann sum, I decided to choose the leftmost point. Sometimes you choose the rightmost, sometimes you choose the middle, but I chose the leftmost point of each partition to evaluate my f of x. And then what I would do is I would multiply my f of x, my height, f of x being the height of my function, times the width of my interval. And that would give me the area of the rectangle. And then I would do this for each integral. And eventually, and some of these leftmost points give you better approximations to the area under the curve than others. Like this one has a lot of extra space. But again, the idea is if I take these more and more intervals that are closer and closer together, eventually I will approach the actual area under the curve. So that was the idea of Riemann sums in one dimension. So now we're going to look at the idea of Riemann sums in 2 dimensions. And the first thing is we're talking about the Riemann sums or double integral over an area. So we're talking about the rectangle in particular that is defined from x equals ab and y equals cd. And what we need to do is we need to partition our rectangle R. And this is kind of a long wordy definition, but essentially a partition of order n, that means we're going to divide up the x axis into n subdivisions or n partitions. We're going to divide up the y-axis into n partitions so that in general we're going to get n squared subrectangles. So here is an example. If we have x going from a to b, y going from c to d, we can partition it up x into all these little partitions, and then we have all these subrectangles. And just a note in this definition, it doesn't say that the rectangles, these subrectangles, have to be the same size. That is not a requirement, but that's really nothing to really worry about right now. And in my example here, I partitioned x into 1, 2, 3, 4 subintervals, and y also into 1, 2, 3, 4 subintervals. So now I get 16 subrectangles for my domain. That is, I've subdivided my rectangular domain into 16 smaller intervals. In the same way here, we divided x into smaller intervals. But now instead of just dividing up a number line, we're dividing up the rectangle. Now that we have our partitions, we're going to let C sub ij be any point in the subrectangle, and we're going to evaluate f at that point. Sort of like here I chose in the interval some point along f of x, that would be my height. This here is in the interval or in the subrectangle, we're going to choose a point, evaluate at f, that's the height now for our volume, and then we're going to multiply, oops, I'm pointing to the wrong formula. They're the same. So here is my f of c for each of my ij's, so each of my subpartitions, and then I'm going to multiply by the area of my subpartition, my subrectangle. And again, the area of my a sub ij is just equal to the change in x times the change in y. So this part is my domain, kind of the base of what I'm going to have for my volume, and f of c sub ij gives me my height over the base, and that's how I get my volume. This is the sum, my Riemann sum, and then if I take the limit as x sub I and y sub j, as these partitions get smaller and smaller as they approach 0, that's going to be my double integral. And finally, we have Fubini's theorem, which says if we're integrating over a rectangle R, which is x from a to b and y from c to d, then the integral where we take the integral with respect to y first and then x second is the same as the integral if we take the integral with respect to x first and then followed by y. Both are equal to this integral of over r with respect to the area A. Now that we've covered our overview slide in some more detail, I should have said overview slides, plural. Now let's do another problem before getting to some review problems. The problem is to evaluate over R y times x cubed minus 12x dx dy, where r is equal to -2 to 1. in the x-axis and 0 to 1 on the y-axis. And note that here f of xy takes on positive and negative values over r. So the first thing I need to do is set up my integral. So I'm going to integrate with respect to x between -2 and 1, and with respect to y between 0 and 1. And here's my function. And again, this is the 0 and 1 are my limits for y, and the -2 and 1 are my limits for x. And just a comment, if for some reason you like to integrate with respect to x first, which often I do, it's okay to integrate with respect to x first. Just make sure you put the limits then for x to go from -2, and then for y, the 0, 1. And there are occasions where one order is easier than the other. In particular, if the inner integral, this part here, or this part here, the first one you evaluate, lets a lot of stuff cancel out. Coming back though to this integral with respect to y first, so my x terms are considered constant, so I just pull them out in front. Derivative of y with respect to y is 1/2 y squared, evaluated at 0, 1, and then my integral is still there as dx. So I plug in my 1 for y, and I get my constant, and I pulled out my 1/2 here. I plug in 0 and I get 0. So this is what I have left to integrate with respect to x. So I finish my integral. I take the integral of x cubed minus 12x. I evaluate at 1 and -1, and I didn't finish doing the arithmetic, but there is my answer. To review what we have done in this video, we looked over double integrals over a rectangular domain. We compared how in one variable calculus, integrals were an area. In multivariable calculus, when we're doing actually 3 dimensions, when we integrate over an area now, our integral will be the volume, because we have the area here of our domain times the height of our function. Our example here was to integrate over r, x squared plus y, over an area where r is the square 0, 1, 0, 1. So we set up our integral. We have our function x squared plus y. X goes from 0 to 1. Y goes from 0 to 1. We integrate the inner integral first with respect to x, since dx is here. So we treat x as our variable and y as a constant. And then once we've integrated, then we come over here and we integrate our outer integral with respect to y, treating now x as a constant and y as our variable. Another look, you can consider this inner integral as, well, like here, when I said we were taking with respect to x, we considered y a constant. So it's like holding y constant and then evaluating the integral, the heights of the function for a constant value of y, and then x. So what you end up with is this area, kind of a plane, a cross section here. And then when you do your integral over y, you start varying y, and you have cross section after cross section for y goes from 0 to 1, and then this integral will sum it all up, and what you get is a volume. Also compared that to Riemann sums, like what we did in one variable calculus, and the idea is that we can divide up our domain into these little subrectangles, and then we can take a height for each of the subrectangles and then multiply it by the length of the rectangle and the height of our rectangle. So kind of the area of the rectangle times the height of our function, and that gives us kind of the volume over each little subrectangle. And as we take the limit, as our subrectangles get smaller and smaller, what we're going to have is our double integral. Last, Fubini's theorem told us that it doesn't matter if we do the integral with respect to x and then y, or if we do with respect to y and then x. Both are the same. They're equal. Both are equal. Now I have 2 problems for you to try. The first is to calculate the volume under the graph of z equals 4 minus x squared minus y squared over the region x goes from -1 to 1, y goes from -1 to 1. The second problem is to find the volume under the graph z equals cosine x sine of y over the region xy such that x is between 0 and pi over 2 and y is between 0 and pi over 4. My suggestion to you is to pause the video, give them a try, and then when you come back, I'll have solutions for you. Here are the solutions. It may be the case for this problem you swapped the order of integration, so you did integral 0 to pi over 4, integral 0 to pi over 2, and then you would have swapped dx, dy. The answer should have been the same. And that is it for this video. Thank you for watching.